Hey, so my name is Ábel. Let me introduce you to forking random manipulations, which is yet another attack against Ethereum. So this is sort of a low-level manipulations against the level 1, where you will bias the leader selection protocol and actually propose more blocks than your fair share. So after that, we will answer the question whether this happened on mainnet or not. So feel free to check out the paper, the GitHub repo, or the follow-up study. How randomness works in proof of stake. So first off, for the goal of randomness is that it must be fair, unpredictable, and trustless. And this is even backed up. Theoretically, a lot of people have come to the conclusion that you need randomness, even in synchronicity, for a secure consensus. Let's spoiler the theoretical results. For someone with 30% of the stakes, can actually propose 32.8% of the blocks, which is roughly 3% more than their fair share. In the middle column, you can see the prior paper's results by Ábel and Weinberg. They only use selfish mixing, and our main contribution in this paper was and we realized that forking attacks can actually help an attacker to manipulate the RANDAO and propose more blocks. Let's recap leader selection. So a lot of you are already know this, but a slot is a 12-second interval. Every slot has a leader who can propose a valid block there. And an epoch is 32 consecutive slots. So after that, we are in this example at the end of the current epoch, and this validator proposes his block. And as you can see, the current and the next epoch's validators are already assigned. But how do we ensure continuity? For this, we will need an attribute called RANDAO reveal. This is the BLS signature of the current epoch number. And this is good because everyone can verify it. And this is one exact value. And only those can know it who have the RANDAO reveal or the private key. If we sort them up, certainly we will get a secure random seed, which we can plug into a pseudo-random generator and get the leaders of epoch E+2. And obviously life goes on, the next epoch starts, and this is going on for eternity, presumably. Let's start with the first attack, selfish mixing. This is sort of a naive attack, even well known before proof of stake. So the idea is that there is a malicious pool who works together and it aims to maximize the profit of the malicious pool. So for this attack, you will need some blocks or some tail slots, and you can actually count what is your profit if you propose your tail slot. Let's count, it's 3. And the main idea is that you have a different option if you have a tail slot. You can actually deliberately miss your tail slot. This will alter the RANDAO seed because this doesn't contribute, because you miss your tail slot and the RANDAO reveal is missing. Only those RANDAO reveals are contributed, which are in the canonical chain. So this messes up the RANDAO seed, the leaders of the next the epoch E+2, and giving us a completely different reward. So let's say it is 6 against 3. So why is this good? Because you have the tail slot and you can pre-compute these two values. So for proposing, you will get 3 in the future, and for missing, you will get 6. Little counterintuitive because you sacrifice or deliberately miss one of your tail slot, but in this price, you can actually get 3 more blocks in the future, compensating for your loss. So this is the idea of selfish mixing. One example of potential selfish mixing. Here in this particular epoch, LIDO proposed all of these tail slots, but he had 8 consecutive tail slots. This means that he could have missed or proposed each of them in 256 different ways. We plotted the number of slots for LIDO in epoch E+2 on the left-hand side. This is a binomial distribution. And on the right-hand side, we subtracted the number of sacrificed slots. So this is the overall reward because we compensated with the sacrificed tail slots. And as you can see, instead of proposing all of them, LIDO could have got 3 more overall blocks in the future. This is particularly dangerous because the more tail slots you have, the more ways you can manipulate the RANDAO. And different objective, which is the target slot utility. Let's imagine a scenario where in a specific slot, there will be some NFT launch, and in this slot, it will contain a really high amount of MEV. And the goal is to grab control over that very slot. And the pool, again, has two options, propose or miss. And the best option is to miss for this pool, because even though you sacrifice an MEV, you can control that very high MEV in the specific slot. Let's go to let's go to excentric reorgs, which are from the paper 3 attacks against Ethereum. This is the main idea of the paper, that we can use this in the context of random manipulations. The setup is that in the middle, in slot n+2, there is the victim of the attack. We will fork out this poor victim by the end of this slide, and you must have at least 20% alpha or the voting power. So this starts, the baseline block is proposed in slot n. Everyone votes for it as the head of the blockchain, and the attack starts where in slot n+1, the attacker privately builds his block and only proposes it to the malicious pool, and everyone votes for it in the malicious pool except for them. So these honest guys, these honest validators actually don't see this and considers this as a missed block. For the same reasons, this victim will start a different fork. He doesn't see this secret block, and everyone votes for it except for our malicious validators. Magical thing is happening in slot n+3, because once you propose this block on time, building upon your secret block, you will get an extra 40% of effective votes. And then let's count the weights or the votes for each of these branches. So 40% coming from the proposer boost, 2 alpha coming from these 2 secret votes. And in the lower branch, 1 minus alpha. And if you do the math, if alpha is larger than 20%, this actually forks out the block in the middle, making the validator slot n+2 really angry because he forked out his block. Okay, so a valid question, why does it matter? Let's imagine for a second that the epoch boundary is between slot n+2 and slot n+3. And this way, as discussed, we cannot do selfish mixing because we don't have the tail slot. But if we fork out this validator with the unknown random reveal, we can actually ignore his random reveal and move on. So let's imagine that in slot n, you have another adversarial slot. You can do selfish mixing there and completely ignore the random reveal in slot n+2. Let's check out a different example. Here we shift the epoch boundary. You have one tail slot. You can propose or miss it. And the first decision in slot 29 is to start forking or not. If you start, as we discussed, we must secretly build this block. And the honest validator starts his independent fork. And in the end, the most natural decision is to finish this forking. Other than that, we will have 2 different options. Both of them include missing your secret block. Again, a little counterintuitive, but it makes sense because they both mix up the RANDAO seed in the end in a different way. So sometimes it is more beneficial. An important attribute is that which of these forks are observable in the beginning of this attack. And the answer is that only the top branch, because this is the only one that doesn't include the random reveal of the honest person in the middle. So we don't have the private key, we cannot pre-compute it, but obviously after they propose it, we can choose the best out of these 3 options. The other option is to publish your block and not start forking. In the end, you can still do selfish mixing by proposing or missing. So all in all, we observe that the attacker has 5 possible outcomes instead of this naive selfish mixing with 2. And what we did in this paper is we analyzed a lot of these configurations and built these decision trees. And the main idea is that you have to find an optimal threshold to compare this value in the upper branch, because this is the only one that can be observed. So this is what we did. We modeled this with Markov decision processes, solved it with value iteration, but I will skip it now because it's really technical. Let's summarize how our attack does. On the x-axis, you can see the stakes of the attacker, and on the y-axis, the actual stakes, so how much of the blocks they can propose with this strategy. So the prior paper's results can actually leverage this by a little with selfish mixing. What we did is double this amount for larger deposited stakes with selfish mixing and forking. And last but not least, the target slot utility, which is where we examine that there is a very valuable slot in the future, and what we examine is the probability that we can propose that slot. So instead of, for example, Lido proposing that block with 29% of the chance, he can leverage that to 40%. Has the RANDAO been manipulated? What we did is analyzed over 150,000 epochs. And the first challenge was to make some mappings between validators to pools. It was a big challenge because we cannot know every single detail of possible candidates of attacks, but we used public entity mappings and actually analyzed for the several largest entities. On the right-hand side, you can see a preliminary result. For these entities, we measured the candidates for possible selfish mixing attacks. And on the lower triangle, you can see that how much of them have missed a slot. We cannot observe any large values, so not a big hopes to find any manipulators. But let's discuss how can we detect random manipulations. For selfish mixing, where you have some tail slots, let's imagine a scenario where this bad pool, this fishy pool, has missed 2 tail slots, and the real question is that was this due to network outage or they acted maliciously, and they have seen these 16 possibilities of missing or proposing these blocks, and this was the best one according to their objective. The issue here is we cannot simulate this fully because in the middle those random reveals are missing. We cannot reproduce them. For forking attacks, this is quite better because even though this block in the middle was forked out, we can still fully simulate it because we have access to the RANDAO reveal. Because of the difficulties mentioned in the previous slide, for selfish mixing we only had statistical approaches, and the idea is that this red line is what we expect from an honest validator, and this histogram is what we measured and they statistically match. A slightly more interesting statistical test by Loránd and Coinbase, we have collected those epochs which had tail slots. So the idea is that if they manipulate, so according to the alternative hypothesis, they miss those tail slots because it was better than the honest option. So it must not come from a binomial distribution. But as you can see, Loránd and Coinbase are not even coming close to this critical 5% value. Okay, for eccentric orgs, we have only found 2 instances. Loránd is the biggest entity who can actually execute such an attack, because notice that for eccentric orgs you need at least 15% of the deposited stakes. So let's go to some future works. In this model, we examine an attacker that aims to maximize the number of proposed blocks, but obviously in reality, not all blocks have the same value. It would be nice to see a work that considers MEV in mind. Can we improve strategies? Are there any crazier combinations of forking and selfish mixing, or even new types of forkings? And the biggest one would be to fix the RANDAO, in my opinion. How much time do I have? 5 minutes? Okay, so I can talk about RANDAO bribery markets. Let's imagine a marketplace where you can trustlessly manipulate the RANDAO together. Multiple small entities can team up and actually sign a smart contract with the RANDAO reveal in it and saying pretty much that, hey guys, do you want me to miss or propose my tail slot? If I propose, I will get the MEV plus the please propose side of the briberies. If I miss, I can still get the miss sides of the briberies. So whichever is greater, I will do that, and the other ones can benefit from this manipulation of the RANDAO. And one more thing about this is that it's quite dangerous because these small entities teaming up can virtually create a big entity, and it's more dangerous. But let's summarize. Why can't we see any manipulations yet? And if it starts tomorrow, can we tolerate the damages? Or will we just lazily social slash the malicious validators? In my opinion, the best would be to have some cryptographic unbiasability, cryptographic guarantees for unbiasability, and not giving them a chance in the first place. And I would like to finish the presentation here, and thank you very much for your attention. Is there any questions?
Can you go a little bit more into detail about your proposals for how to fix RANDAO?
There are candidates, but in this work we only analyze the potential damages of this work. But verifiable delay functions are obviously one candidate considered by Ethereum Foundation, if I'm not being mistaken.
I have a question for you. You've presented a very good scientific analysis with one major flaw. The assumption that LiDAR is a single entity. Can you explain why you have this assumption?
We analyzed all of the entities, so we did no exceptions. So you guys were the biggest fans, so obviously we had to do that as well. This is a really good question.
Yeah, but you are aware of the fact that LiDAR
Yes.
is a decentralized entity controlled by multiple operators. Some of them were even included in your list as separate entities, like
Yes.
Bitcoin Swiss, for example.
Yeah, we had to exclude the possibility of any malicious acting, but we are aware of that, yes.
Yeah, well, from my side, the only suggestion would be to analyze each node operator one by one, taking into account the fact that even if you have 8 slots in a row by a single entity called LiDAR, it doesn't mean that these 8 slots are controlled by single entities for real. They might be. They will most likely be controlled by several node operators who are independent and are very less likely to make a so-called co-deal. Because if you assume that, you can easily assume that Coinbase and Binance can also make a co-deal, and then you should join them in the analysis.
Yeah, we are not trying to attack anyone. Just
yeah,
it's not a conspiracy theory, but we excluded this possibility. No?
Okay.
Okay.
Is there any other question?
Okay. Thank you for your attention.
Thank you.